What if our computers could learn not just by being coded, but by experiencing things the way our own brains do? Well, that's not science fiction. It's the incredible promise of something called neuromorphic computing. And believe me, it's a field that's set to change pretty much everything we know about intelligence itself. So, to really get what we're talking about, let me just start with a simple question. When you think of the most powerful computer in the world, what pops into your head? Is it one of those gigantic supercomputers? The ones that fill an entire room, all humming away in some high-tech lab? Well, the real answer is actually a lot closer to home. In fact, you're using it this very second to process my voice and understand everything on the screen. Yep, you guessed it, it's the human brain. And here's where it gets really wild. Just look at this gap in efficiency. Your brain, it runs on about 20 watts of power. That's less than a dim light bulb. And with that, it learns, it adapts, it can spot a friend's face in a crowd in a split second. A supercomputer, on the other hand, needs millions of watts, and it can only do what it's been programmed to do step by step. It completely chokes on the kind of fuzzy, messy information our brains handle all day long. This right here, this is the core problem that neuromorphic computing is trying to fix. Okay, so let's get into it. To really see why we need these brain-inspired computers, we first have to understand how our current computers think, and more importantly, why they're starting to hit a wall, a kind of digital bottleneck. For the last 70-plus years, pretty much every digital device you've ever touched has been based on this one core design, the von Neumann architecture. And the key thing to know is super simple. The part that does the thinking, the CPU, is physically separate from the part that holds the information, the memory. And this is the perfect analogy for the problem. Imagine you've got this brilliant, world-class chef. That's your processor. But to cook, the chef has to stop, leave the kitchen, and run down a long hallway to a pantry, that's your memory, for every single little ingredient, one at a time. It doesn't matter how fast that chef is, right? All that running back and forth creates a huge traffic jam. And that, in a nutshell, is the von Neumann bottleneck. This constant back and forth, this fetch and execute cycle, it's happening billions of times every single second inside your laptop or your phone. The processor is always grabbing a piece of data from memory, doing one tiny thing with it, and then going all the way back for the next piece. This endless data shuttle is what eats up most of the time, and an absolutely staggering amount of energy in all of modern computing. So what's the alternative? Well, it's a completely different way of thinking. It's about creating silicon that's built from the ground up to think differently, literally a brain on a chip. And this brings us to neuromorphic computing. Now, this isn't just about writing smarter software to run on the same old hardware. No, this is about building totally new hardware that's physically modeled on the brain's incredible structure. In this new model, that whole separation between the processor and the memory, it's gone. They are woven together into one dense network, just like the neurons and synapses in our own heads. So our chef doesn't have to run to the pantry anymore, because all the ingredients are right there at the cooking station, exactly where they're needed. This chart really lays it all out. Traditional computers, right, they're inspired by logic and math. They've got those separate parts, and data flows one step at a time. Neuromorphic chips are inspired by biology. Everything's integrated, and information flows in this massive parallel web. It means millions of things can happen all at once. And see that event-driven part? That's key. It means it only uses power when a neuron actually fires, just like a real brain, so it's incredibly efficient. Okay, so what's the actual payoff here? Why go through all the trouble of this radical redesign? What are the real advantages of making a computer that thinks more like us? First off, the efficiency is just mind-blowing. Because you get rid of that data bottleneck completely, these neuromorphic chips can be up to 1,000 times more energy efficient for certain tasks. 1,000 times. And then there's the speed. For the kind of stuff our brains are amazing at, like finding a tiny pattern in a mountain of messy, noisy data, the speed up is almost hard to wrap your head around. We are talking millions of times faster. This isn't just about making your spreadsheets run faster. This is about solving problems that are basically impossible today. So the bottom line is this. You unlock these huge energy savings, incredible speed for AI, and because they're built like a brain, they're way more resilient. If one little part fails, the whole network just kind of works around it. And maybe the coolest part of all, they can learn and adapt as they go without needing to be completely reprogrammed from scratch. Now, this all sounds amazing, I know, but we're still very much in the early days of this technology. So let's talk about the incredible future promised, but also the very real problems we still have to solve to get there. The potential applications are straight out of a movie. I mean, imagine an AI assistant that actually understands context and nuance, not just commands. Or think of medical sensors that could diagnose a disease instantly, on the spot. Robots that learn from their environment like a toddler does. Smart devices everywhere that could run for years on a single tiny battery.
But okay, let's bring it back to reality for a second. This is a very new frontier. We are deep in the research and development phase right now, so don't go looking for a neuromorphic chip in your next smartphone just yet.
And maybe the biggest hurdle of all isn't even the hardware itself, it's the software. I mean, think about it. We've spent over 70 years getting really, really good at telling traditional computers what to do. You can't just take that code and run it on a chip that thinks like a brain. We literally have to invent entirely new ways to program and talk to these new silicon minds. Which leaves us with a final, really fascinating question to ponder. For decades, we've been teaching our machines how to calculate. Now we're just starting to teach them how to perceive, how to learn. As this technology grows up, and as silicon starts to truly adapt and think more like we do, you just have to wonder, what will it dream of?